I'm also going to give a talk about data-type-generic programming in Agda. So this will probably sound very familiar to you. There are two keywords in this title that are important. One is practical. I am going to explain what we mean by practical and try to convince you that our approach is practical in the sense that we mean. And the other one is native data type. So also we want to actually bring data type generic programming to the native data type part of Agda. And another keyword that is perhaps missing is safe. What we really focused on in this work is to have actually a way to define data type generic construction safely. That is, once they are implemented, you know that they will always work regardless of which data type you use them on. So I assume by now most of you know what data type generic programming is. And so I'm just going to summarize by saying that it is the art of defining constructions or programs that can be applied to any data type using a single implementation. And so the benefits are quickly visible. So you avoid code duplication, and also you kind of get consistent behavior by having a single implementation. And I think one of the most common example in FP circles is the use of deriving in Haskell. I think most people that have used Haskell know the benefits of simply being able to derive so many constructions for free, essentially, as soon as you introduce your own data type. And so they can be very simple, like the ability to debug, to print values of your data type, but they can get quite intricate, and especially with generics, you are able to derive for free many quite involved constructions. And so a fair question would be, that's interesting in Haskell, but why would you need this kind of construction in Agda or proof assistance? And so a simple answer would be, well, there are programming languages in their own rights, and so the constructions I just mentioned are useful. But there are actually many generic constructions that are very interesting and useful when you're trying to prove things about data types. So most of you probably know that you always have an induction principle that comes with any data type. And there are actually other generic constructions that exist in the same kind of way. And some of them are introduced in a paper called The Few Constructions on Constructors. And essentially, in this paper, it explains that there is a recipe for defining them for any single data type. Like there is a systematic way to define them at the meta level. And so then it's only a matter of having a system to derive them automatically. Another very common example in Agda in particular is decidable equality. Rather than have a Boolean equality on values of the data type you have, it's way more interesting to actually get a witness that two values are equal or a proof that they are distinct. And of course, like there are other examples that we can find in the wild. And I've shown a bit of an example like of Agda code. So this is an indexed parameterized data type. And it's usual to want to derive decidable equality, as I said, and you kind of would like your language to always give this to you. That is, assuming some decidable equality on A, be able to give you decidable equality on your data type parameterized by A. And likewise, you kind of expect to have this induction principle. And in Cock, you do. Like when you define an inductive data type in Cock, you will get this kind of elimination principle for free. In Agda, it's not the case. And so what is the solution if your language doesn't give you any deriving primitive? There are mostly two approaches. So as you just saw, there is a thing called elaborator reflection in Agda. A fair comparison would be template Haskell. That is, like you are able to manipulate internal syntax, and under the condition that the type checker accepts the terms you produce, you are able to define pretty much anything. And so it is a very powerful mechanism. It allows you to essentially produce definitions that look just like if they were handwritten, but it's very hard to implement using reflection code. It's very verbose. You have to be very careful about the transformations you do on terms. For example, you have to use the Brown indices, and it's usually hard to ensure that you don't do any mistakes. And of course, it's hard to guarantees that you have correctness properties, because you can only know if your code fails once you instantiate it for a given data type. And so it's hard to ensure that our implementation is correct. And so the other well-known approach is to use what is called universes of descriptions. So the idea is you internalize, like you make explicit what it is to be a data type, and you work inside an encoding of data types. So usually you start by introducing what is a description. You interpret the description as a shape functor. And if you take the least fixed point of this functor, you end up with a type, an ACDA type, that behaves pretty much like a native data type that you're trying to describe. And so when you use this kind of encoding, it's very easy to define data type generic constructions. You essentially quantify over all the descriptions and then prove properties about mu of D. And so, like, generic constructions are regular ACDA functions, and there is no trick to it. Once it's implemented, you know it will be correct. But of course, you are proving properties about mu of D and not native ACDA data types. And so as soon as you want to derive generic properties, you have to work with this explicit encoding, and it's generally not very practical. And so our goal is to find how to bring this kind of universe of descriptions and like the benefits of it closer to what native data types are, so that we are able to define generic constructions that do not operate on mu of D, but on native data types, and that are correct by definition. So yeah, with this in mind, our goal was to make an ACDA library with two targets in mind. The first target was library implementers. We wanted to provide safe, reusable primitives to implement data type generic constructions. And of course, we wanted to actually implement constructions to demonstrate that this is a practical approach for regular ACDA users. And so we also had pretty strict constraints. We wanted to avoid using reflection at all to define generic constructions. And so this was a challenge that we had to face. And we also wanted to be safe, to be in the safe fragment of ACDA. And this means that we really had to convince ACDA that all our definitions were terminating, which usually is an issue that you have to deal with when you work with this kind of encodings. And also we wanted to have user-friendly constructions. That is, generic constructions that have the proper type that you would expect if you had written it by hand. And we wanted to have them well-behaved. That is, that they should compute and reduce as you would expect them to. And so I'm glad to say that we succeeded. We have a library that does this kind of stuff. And so assuming you have installed it, so you just import it, and you have to derive an encoding of data types you want to have constructions over. So this is a macro. And this is the only place where you actually use reflection. And then once you have this encoding of your data type, you can use all the constructions available in the library. And so the first one we implemented is, of course, the generic induction principle. And so I have to confess that maybe the name isn't quite what it should be. It's called derivaling, but we're not generating code. Like, it is a regular ACDA function that happens to take an encoding as an argument, and that will compute the appropriate type once it gets its first argument. And so we can see that applied to the description of natural numbers, you will end up with a function that is precisely the eliminator that you would expect. And applied to other descriptions, you end up with a very systematic and actually useful type. And all this without using reflection. That means that it's just a regular function. And a very important thing that we wanted to enforce was proper computational behavior. So we see here that we define the addition of natural numbers using the eliminator that we derived. And we see that it is able to make progress on open terms. So if you see like the add s definition, so n is a free variable, And if we apply add to suc_n, it is able to move the suc out of the addition. So this is very important because it allows you to actually use these constructions inside proofs. And there have been attempts to do this kind of stuff in Agda, and computational behavior was always like the missing part. And actually, like I want to emphasize that here I've written the types explicitly, but you don't have to do it, and you don't actually have to make these aliases. Like every time you just want to use an elimination principle, you just have to call derive elim and give it the description. So I think it is pretty useful. And so we also implemented decidable equality. So we have a derived decag function. Again, it's just a function. And if you give it the description of natural numbers, you end up with what you expect. And it is able to fetch the appropriate dependencies. So, for example, like on vectors, it will ask for decidable equality on some parameter A. And another construction that is very useful is a proof of disjointness of constructors. You always have the property that distinct constructors are unequal, but you have to prove it yourself. And this involves as many functions as you have pairs of constructors. And here, with a single implementation, no confusion, we're able to prove all these properties. So you see that the two first definitions show that suc is different than 0, and we use a single implementation. And again, like we are able to prove that suc is injective using the same implementation. So I'm just going to give some idea of the technical challenges that we had to face to implement this library. So we had to find a very precise encoding of telescopes to account for what parameters are and indices are. And so we ended up with a first-order encoding of telescopes with induction recursion. And then we had to also enforce a first-order encoding of data type descriptions. And then the question was how to bridge the gap between this encoding of data types and actual Agda native data types. And what we quickly realized was that you should avoid taking the fixed point and implementing construction on that. And rather, the only thing you're interested in is the ability to inspect a value of a native data type and to see what was the constructor that was used and what were its arguments. And so what we derive in the encoding is only shallow conversion functions. That is, for some value of type A, we are able to know where it came from, and we are able to do the reverse transformation. And another key ingredient was accessibility predicate. So if you are only able to split a value into its arguments and constructor, there is no syntactical relationship between the arguments that you get and the initial value. And so Agda will not allow you to recurse and do this many times. And so you have to find a way to convince Agda to do this kind of stuff. And so the key insight was to introduce a Datatype-generic accessibility predicate that we derive during the encoding. And so it guarantees that any value is well-founded. And then we had to implement the construction that I just showed, again, with no reflection, and that are correct by definition. So yeah, it's the only bit of the library code that I'm going to show. So this is the content of the asdesk record. And have you seen, like it only contains the description, conversion functions, and this accessibility predicate. And that's all that was needed to implement all the constructions that I've showcased. And so yeah, this library is available, and it mostly works. And I think it is a good example, or at least it proves that user-friendliness is not exclusive with safety, and that you can actually have generic constructions that are safe and generic, and that still are usable. But I mean, there are, of course, more to do. We don't support nested types, and we don't support all the Agda data types, mostly because Agda supports a lot of data types. And we are, of course, interested in the finer encoding. Personally, I've been trying to find a better representation of telescopes to account for dependencies right now our telescope at a given position gives access to all the preceding values in the telescope, and I actually want something finer. And yeah, like we are happy actually that there is other work being done in data type generic programming. So the last talk, of course, is very interesting, and we are very much looking forward to find how to merge the work that we did to maybe make a good library out of the two. So yeah, thank you for listening. And